Okay. Yeah, it's our pleasure to have Lorenzo here in our seminar to share his work on learning efficient decoders for quasi-chaotic quantum scramblers. And yeah, I think it's like Lorenzo, you can like take up the floor.
Oh, thanks very much for the introduction, and thanks for having invited me, actually. So my name is Lorenzo Leone, and I'm a PhD student at the University of Massachusetts, Boston. But this work has been made by us also when we were visiting the Los Alamos National Laboratory with their learning skills. It would be particularly useful. So in the title, you can see the appearance of three concepts which often appear in quantum mechanics, which is the concept of learning, quantum chaos, and scrambling, which is a concept introduced kind of a decade ago or so. And I will try to, glue them together in a coherent fashion, let's say. Okay, so let me first acknowledge the co-authors of this work. So this work has been made in collaboration with my advisor, of course, Alyosha, who moved to Naples recently, and that's why I'm in Naples. Otherwise, it would have been impossible to talk for Singapore, because 12 hours different between Boston and Singapore would have been a problem. And then there is my PhD mate, who is graduating soon with me, Salvatore Oliviero, and our mentor, Seth Lloyd. So we put out two papers. The first one is a simplified letter, making some simplifying assumption, which is meant to a broader audience, while the second is the technical embed one for a tightest audience. So let me first introduce what's the setup. So of course, this is a story about scrambling, and scrambling is a unitary process. So imagine that you have a localized quantum information on a subsystem of qubits A, which has local correlation, of course. And then this undergoes a unitary evolution in a bigger space. And if this unitary evolution is said to be scrambling, if when measured the output of this unitary, you are not able to retrieve the local information by local measurements. So the tale is that the scrambling is hiding local information into non-local degrees of freedom. In order to retrieve some pieces of the original information, you need to do global measurements. And then the question is, can I recover this spreaded information? And the answer can be trivially yes, because the process is unitary. So you just apply the Dagger unitary and retrieve and localize the information again. However, irreversibility in quantum mechanics arises for our ignorance of the unitary evolution. We don't know what is the unitary evolution, so in general, it can be hard to undo this unitary evolution and localize the information again. And since the unitary scrambling, you can even hope to retrieve the information by global measurement because they are too many, and so you don't know how to do. So let me introduce what I mean by learning in quantum mechanics. Now I'm not talking about quantum learning theory. Quantum learning theory is a well-established theory that borrows its roots from classical learning theory. But the learning I'm talking about is slightly different. So maybe the setup is the same. But the rules of the game are very different. So the setup, imagine you have an unknown unitary U, and you have query access to U, which means that you apply this black box wherever you want on a big quantum register. You can do whatever you want. And then by measurements or expectation values, you just acquire classical or quantum information. Acquiring quantum information means that just you save in some QRAM your quantum state, and then you use it later. This is a very general setup. Then what is your task? Your task can be of two kinds. First, you have access to this black box, black unitary, and then your task is to synthesize or learn how to synthesize this unitary after a while that you don't have access to this black box anymore. Or you can require a weaker task, which is learn some properties of U in order to achieve some task. For example, the unscramble information. So your task is to localize or learn how to localize the information on the A subsystem back again. Or a weaker one can be that you are given query access to a unitary who entangles some state, let's say some product state. The unitary entangle the product state, and your only task is to disentangle the given state in a given partition. So you don't even ask to learn the product state. You just ask to disentangle the state. This can be another weaker task. Of course, if you're able to synthesize the unit in a quantum device, you are also able to unscramble the information to disentangle states and blah, blah, blah. So the second task is weaker than the first one. And the rule of the game are do whatever you can. I think that learning in quantum mechanics needs fantasy, a lot of fantasy, because there are many protocols that we can apply, and we need to do so, because at the end, tasks justify means, as Niccolò Machiavelli taught us in 16th century. So one thing that I would like to claim is that learning in quantum mechanics is a positive concept. I'm talking about no-go theorems. We see no-go theorems outside. There are many no-go theorems, and they are very easy to prove in some sense. If you have very strong setup, they are not so difficult to prove. But no-go theorems are useful because at least you know what you cannot do, but are fragile. Because let me explain what I mean. If I have a method M that I discovered that cannot learn the unitary U, I'm not saying that U is complex in some way. What I'm saying is that the method M is not suitable for you to learn U. In the opposite case, and that's why it's a positive statement learning quantum mechanics, if the method M can learn the unitary U, then U is in this sense of learning non-complex. Of course, can learn means efficiently in terms of computational resources. Okay, well, let me explain why I arrived to this way of thinking. Because 2 or 3 years ago, people proved that if you use VQA, you cannot learn Clifford circuits. VQA are just variational quantum algorithm, which, you just have many gates that are parameterized by angles. And so you have a landscape of unitaries that you can tune and you can classically optimize. And people discovered that this would entail barren plateaus, which means that it's very difficult, it's very hard to extract useful information and tune these parameters to learn a Clifford circuit. Okay, similarly, always a couple of years ago, people discovered that Clifford circuit cannot be probably approximate correct learned if you have access to the output distribution created by this Clifford circuit acting on computational basis states. So the compilation fails. However, 10 years ago or so, Lowe discovered that it's very efficient to learn Clifford circuit. You just need to do Bell measurements, and learning Clifford and synthesize Clifford, save it in memory, in a classical memory, and then synthesize it in the future requires just polynomial resources, which goes as n cubed. I'm saying this because the fact that the Clifford group can be efficiently learned and synthesized will be the core of the algorithm I'm going to show. So it will be the basic assumption. The basic assumption is that Clifford is easy, can be simulated, can be encoded classic, and can be learned very efficiently. Okay. Let me now outline the rest of the talk. So first, I will bore you with some technical slide with the Pauli group and the Clifford group. For those of you who are not familiar with this concept, can be useful, I hope. Then we have, I will talk again and again about scrambling, the characterization of scrambling. I will also claim the Clifford group, the Clifford circuits are very good scrambler in general. Then I will introduce the playground of the learning algorithm, which is the decoupling theorem, which has been introduced by Hayden and Preskill and then elaborated by Yoshida Kitaev. That's why, for me, it's just Hayden, Preskill, Yoshida Kitaev protocol. And then I will turn to describe the main results of the paper, which are, Okay, we can unscramble, otherwise I wouldn't be here. We can unscramble all the information without knowing you. And the very fun fact is that we can unscramble information by using only Clifford resources, even if the scramblers are quasi-chaotic. And I will explain to you what I mean, at least, by quasi-chaotic scramble. And then I give a proof sketch. And whenever I can do some simplifying assumption, I will do so for the sake of clarity and avoiding technicalities of the discussion. Okay, so the boring slide about the Clifford group. Okay, in order to define a Clifford group, we first need to pass through the poly group, which is the group generated by all the products of sigma x and sigma z on every qubits. So these are called generators. These are 2n generators, and they generate a group whose cardinality, which means how many elements the group possesses, is 2 to the 2n. But from now on, 2 to the n, which is the dimension of the Hilbert space of n qubits, will be D. Okay. Analogously, you can take the products of all the sigma s and sigma z on the A subsystem and generate the local polygroup on A. Of course, the dimension of the local polygroup on A will be dA squared. Okay, cool. Now we can define the Clifford group. The Clifford group is filled by those unitary operators whose adjoint action on polystring, on every polystring, returns an element of the polygroup, so another polystring. Polystring and poly operators for me are completely the same at the moment. When I talk polystring, poly operators, they are just elements of the polygroup. Okay, it's also useful for the sake of the clarity of scrambling and blah, 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 to define a Clifford group being the set of unitaries generated by these three elementary gates. The first one, and the most important, I guess, is the C0 gate, which is a 2-qubit gate. You can see it because it's a 4x4 matrix. And it is one responsible from the fact that the Clifford group is very good at entangling. Then you have the Hadamard gate, which creates superposition in the computational basis, and then the S gate here, which puts this I phase on the 1 bit. It is very famous, the result from Gottsam and Neal almost 30 years ago that says that the classical simulation of quantum computation that includes Clifford circuit and input in computational basis and measurements in computational basis can be entirely replicated and simulated classically in polynomial time. Thanks God, the Clifford group is non-universal to quantum computation. So the set of gates C0, H, and S cannot create any unitary in the unitary group. But to make this group universal to quantum computation, you just need to add one non-Clifford gate. Can be whatever you want. But typically people take the T gate because it's the simplest one, because it's a single qubit gate, diagonal in the Z basis, which is very similar to the S gate. But instead of I, you have this e to the I pi over 4 phase on the 1 bit. It is instructive to see that the T gate is not a Clifford circuit. And in the way to see it, just apply the T gate on a sigma x, and you see that it gives you a superposition of sigma x and sigma y. So instead of giving you a single poly operators, it gives you a superposition of poly operators. So, and this is exactly the reason why quantum computation, including T, number T of non-Clifford of T gates, cannot be simulated via a polynomial algorithm, but exponential algorithm in T, because you need to take care in some way on all those branches of poly operators. So, for example, 1 T gate create superposition of 2 poly operators, 2 T gates, 4 poly operators, and so on and so forth. So, as you can see, the proliferation is exponential, and classical simulation must need to take into account this exponential growth in proliferation in the poly basis. Okay, so only Clifford circuit polluted with a logarithmic number of non-Clifford gates can be simulated classically. And this will be useful during the talk to take this in mind. Okay, now let's turn to talk about scrambling. Okay, Again, scrambling is the tail of scrambling is that you have a localized information and a scrambling unitary hide this local information into a bigger subsystem, so no local degrees of freedom. But of course, this is a definition. What is useful is a characterization of scrambling unitaries made in this paper by Roberts and Yoshida in 2017 that proved that a unitary is scrambling if and only if a out of time order correlation function is very small, is exponentially small in number of qubits. So what's this out of time order correlation function? Consider two local operators A and D, which initially commute because they are spatially local and concentrated in the system A and D. And then you start evolving D with the unit adjointly, of course, because it's an operator, adjointly with your unitary. If this unitary depends on time, the support of this D will grow and eventually will not commute anymore with A. Then use your out of time order correlation is just that you place in this alternating fashion these two operators, one not evolving time A and the other evolving time D of U. And you just compute the expectation value of this non-Hermitian operator over the identity of the maximally mixed state, identity over D. Then Roberts and Yoshida proved that if this function, which is a function of U, is attains the scrambling value, which is exponentially small in a number of qubits, remember that D means 2 to the n, then the unitary is scrambling. Cool. This is very useful because it allows you to characterize scrambling unitary by just looking at one single scalar function. From this, we can claim that the Clifford circuit are very good scrambler typically. Indeed, if you compute the average over the Clifford group of this 4-point TOC, you get the scrambling value. Similarly to the 4-point TOC, you can also define higher point functions, always in the same fashion. You just put these alternating operators and compute the expectation value over the maximally mixed state. One particularly non-trivial is the 8-point TOC, because if you compute the typical value of the 8-point TOC for Clifford circuit, it differs significantly from the value of a general unitary in the Clifford group. I'm keeping claiming that the average is a typical value. Yes, the average is a typical value because you can prove Chebyshev bounds and concentration bounds. If you pick a random Clifford operator, it will obtain this value with overwhelming probability. And the same, of course, holds for the unitary operations. Now, why this OTOC is important? Because it turned out that this 8-point OTOC quantifies the complexity of a scrambling unitary, not the fact that they are complex. So in order to study the transition in the complexity of this scrambling, so in the value of the 8-point OTOC, since a Clifford group attains 1 over D squared, in order to reach this value, you need to add some non-Clifford gate in some way. So we decided to study this Clifford circuit plus T non-Clifford gates and the transition towards the value of the universal 8-point TOC. So first, we can say that these circuits are scrambler for every T. So if you pick one of these circuits at random, it will be very scrambling. So the 4-point TOC have the value of the scrambling unitary. Then how this circuit is built out. So imagine that you have a very deep Clifford circuit, and then you start adding more Clifford gates, this orange one, polluted with a finite number of T gates here in blue. Here you can identify 3 regions. The first one is the classical region. It's a classical region because the number of T gates is logarithmic growing with the number of qubits, and so we know that we can simulate this ensemble of circuits very efficiently in a classical way. And indeed, if you look at the value of the 8-point TOC, you realize that this value is the same of the Clifford group up to a polynomial overhead, which is not decreasing the exponential behavior in n. Then, if you pass this barrier of logarithmic number and you go and your number of T gates start scaling with n, but being strictly less than n, you have this quasi-chaotic region. in which your 8-point OTOC is 1 over d cubed, which is very different from the value of the 8-point OTOC for universal circuit. And indeed, we will see that this will be the play region for our algorithm, the region that we didn't expect to see. Then if your number of T-gates scales with n, but are more than n, you pass this barrier, you go towards the chaotic circuits, which are basically indistinguishable from our random circuits, and attains the value 1 over d to the 4th power. We will come back to this diagram after presenting the algorithm or the main result. Okay. Now it's time to introduce the learning playground of the scrambling unitary, which differs a bit from the usual tale of scrambling, in which you have a localized information and this gets spread throughout the system. You're required to acquire this information by reading the output. Here we always talk about scrambling destroying local correlation, but we have two parties, the party Alice and the party Bob. Imagine that both Alice and Bob possess an APR pair, which is the maximally correlated state between two set of qubits. So let's say that Alice has this APR pair R and A. Oh, by the way, the definition of APR pair, which is a Bell state, is up here. Okay, so R and A are two subsystems of qubits that has the same number of qubits, the same BB prime. So Alice possesses this APR pair RA and Bob possesses BB prime. And both Alice and Bob, a branch of their APR pair, is common with the input of a scrambling unitary UT. Mind that this T is not the time, but just a number of T gates thrown in this scrambler here, which is Clifford, plus T gates. So this horizontal line from now on will represent APR pair. I hope that these drawings will help during the talk. So as you can see, initially, Alice has this maximally correlated state with the input of a scrambler and also Bob. And then A and B undergoes this scrambling evolution. So scrambling evolution is supposed to destroy local correlation, possessed in A and possessed in B. So you can ask, what is the mutual information between Alice, which is now is represented by R, and Bob, B prime, if Bob looks at any subsystem, say D, of the output of the scrambler? Okay, the answer is, proved by Aden and Preskin in 2007, that provided that D is slightly bigger than the number of qubits in A, so it's just logarithmic growing with respect to A, the mutual information between R and DB prime is maximal. It's greater, the maximal value is A, so the number of qubits in A, and is lower bounded by A minus a very small number. This is referred to as the decoupling theorem. So the scrambling unitary has destroyed local correlation between R and A, and all the information flew towards D and B prime. So in principle, there should exist a protocol that Bob can use by measuring the subsystem D and recover all the information that in Alice's possession. In other words, Bob must build up a protocol and build up a decoder by reading some output, which is very small or the size of A of the scrambler, in order to retrieve all the information thrown by Alice. But the take-home message that will be important to understand the proof of the algorithm is that Bob can look at any subsystem of the output, because thanks to the scrambling properties, scrambling destroyed all the local correlations. So no matter what the system is, the important thing is the size of the subsystem you look at. So there should exist a protocol. Indeed, the protocol exists and has been invented a couple of years later by Yoshida and Kitaev. So first of all, let me clarify what is the task of this protocol. So since we are playing around with Bell pair, the task of the protocol is to create maximal correlation, so a Bell pair, between Alice, represented now by R, and a mocking system R prime, which has the same dimension of R. And this R prime must be in Bob possession within the Bob's qubit. So the protocol is the following, is straightforward. So Bob first creates this mocking APR pair between R prime, the system he wants to create maximal correlation with, and A prime. Then apply on his qubits B prime and A prime a decoder, which will be the core of the algorithm. What this decoder looks like is what we are about to learn, which is unitary. And then he measured in the Bell basis. That's why there is this legs here again. And then if they claim that for suitable decoders V, this protocol allows Bob to create maximal correlation between R and R prime. Okay, so let us give a look to what this decoder should look like. So once when we studied this protocol for a long time, and once I ran to my friend Salvatore Olivero, the co-author, and I said, Salvatore, I had a beautiful idea. Let's try to put a random decoder and see what happens. Maybe it will unscramble the information. Of course, that was a very bad idea without no reason, but you know, sometimes people are crazy. Indeed, the fidelity is very bad. It's the same fidelity as you pick two random states in the Hilbert space of A and compute the overlap. It's the same exactly fidelity, so it's very bad. However, what is the type of decoder that attains very good fidelity with the target APR pair RR prime? Well, of course, there is the inverse unitary evolution, the dagger. Here you have the star, not the dagger, but this is a technical reason due to the APR pair. The properties on a branch is the dagger, on the other branch is the star. So just think about this decoder as being the dagger, the inverse unitary evolution. So the inverse unitary evolution attains very, very good fidelity, 1 minus very small number, but it is unsatisfactory because it requires the complete knowledge of you. But in general, Bob does not know it's pretty unsatisfactory that Bob knows everything about you. Bob needs to learn something about you from the subsystem in reading from. But so the main question of the work is UDagger the only unitary in order to do the job? And how hard is for Bob learn another decoder V? Before answering this question, I want to give you a cartoonized proof of why UDagger does the job of unscrambling information with this protocol. So remember that every line is an APR pair which create maximally correlation between two systems. So at the beginning, without this unitary, Alice possessed maximally correlation with A. Then Hayden and Preskill proved that the mutual information between R, D, and B prime is maximal. So all the information from A flew towards D. And now there is maximal correlation between R, D, and B prime. But imagine that there is maximal correlation only with R and D. This is why the cartoonized version. Now, since Bob measures in the APR pair D prime, the maximal correlation is with R and D prime because information flow towards this APR leg. Now, with the dagger unitary evolution, what the dagger unitary evolution can do is just, flew back again the information from D prime towards A prime. And the existence of this APR pair makes maximal correlation between R prime and R. So that's why the dagger unit evolution works with this protocol. Of course, there is a rigorous proof of this statement. This is not rigorous at all. Okay, so our playground will be, can Bob, with a finite amount of query accesses to the scrambler UT, and reading only the system D that possess maximally correlation with R prime, find a suitable decoder V to unscramble the information without being UDagger? okay, let me give first the result and then the proof, and in the middle, I think is the right spot for maybe some questions. The main claim is yes, Bob can learn with an algorithm, this decoder V, provided that the number of T gates in this scrambler is strictly less than n. So now makes sense the diagram we looked at before. So there exists this algorithm which runs in polynomial time in n, but exponentially in the number of T gates, that learns V, a decoder, how being a Clifford decoder V, then scramble information with maximum fidelity and with probability, which is 1 minus an exponentially small number. So if we look again at that phases of this doped circuit, now they make sense, because the first region is classical, because I can simulate those circuits classically, and the Clifford decoding in this protocol can be done, and it's also efficient because it runs in polynomial time, because the number of T gates are log n. In the quasi-chaotic regime, the surprising thing is that the Clifford decoding is robust in this, so it survives in this quasi-chaotic phase, although the algorithm runs in exponential time. But for now, I don't care, because how is that possible? That this region admits a Clifford decoding. I will explain you why. And then if you cross the number of T gates equal n, then both or the fidelity, either the fidelity or the probability of or the probability of recovering go exponentially to 0. And I will show you why after n t equal n, all the algorithm goes very bad until it reaches fidelity 0 and probability 0 in the chaotic regime, whereas no Clifford decoding, no algorithm cost is present. Okay, the rest of the talk will be devoted to some proof or proof of sense of why this algorithm is true. So I think that now it's a good spot for questions, if you have some. Otherwise, I will keep proving this algorithm.
Yeah, so for the audience, if you have questions, either you can type it on the chat, or you can just raise your hand and unmute yourself and ask the questions. But in the meantime, actually, I do have a question for you. So when you can you go to like one slide back, like to the, yeah, this one. So over here, basically, you kind of like show the propagation of the informations from like R to R primes, right? And it's kind of like seems a lot to me of like quantum teleportations, and I'm just wondering how this is related to quantum teleportations.
Extremely related.
Okay. So
It's yes, indeed, this protocol
mm-hmm.
has been used in quantum teleportation a lot. This is actually is borrowed from quantum teleportation. So people, when they talk about these diagrams, they talk about the black hole scrambling, because, you know, you can play with complex unitaries saying that they are black hole, and also we play around with it. But actually, the rigorous and maybe sense, this makes sense exactly in protocol quantum teleportation. There are applications of this setup in quantum teleportation when you have bell pairs, scrambling unitary that follow information around and stuff. That's why this learning can be used by an adversary that is reading in some way the output of a quantum teleportation protocol. So yeah, this algorithm plays a role there.
Right. Okay. Yeah, as in the other question that I have is a bit more generic. At the beginning of your presentations, you mentioned the discrepancy between learning the distributions of the Clifford circuits, like that metric element, for example, and the simulations of the like Clifford circuit using classical computers. Like, do you kind of have an intuitive way of understanding why this discrepancy like coming up from? Because like if we be able to kind of like simulate the Clifford circuit, then we should be able to like use the information and learn the distribution effectively. But why like couldn't we learn it the distributions? Yeah. So it's a bit more generic, like
Yeah. So first of all, here we are talking about only learning the distribution, because
okay.
I have the same intuition of you. If I can learn something, if I can simulate something, I can also learn something. Indeed, it's true. Clifford circuit can be learned efficiently. Well, now, why cannot be learned by the output distribution? I don't have the rigorous question, but my feeling is that the output distribution includes very, very small numbers.
Mm.
And so maybe it's the sensitive of your measurement about these numbers. Whenever you do Bell measurements, those numbers becomes plus and minus 1. That's why I think in a very efficient way, you can distinguish between plus and minus 1. And that's why you can go down in learning. And maybe the output distribution, since you use a single copy, the expectation value is exponentially small. And so maybe this is why. At least this is the reason in VQAs. In output distribution, I don't know very well the reason. It should be something like that, because you still there, you use a single copy of your unitary.
Right. Okay. Yeah. Got it. Yeah. I think like there's no question from the audience, so maybe you can continue and we
Yeah.
just
Sure. Okay.
Yeah, thanks.
Yeah. So so I will prove the statement. So we need to take some step back. Okay. So remember, at the beginning, you have Alice and Bob both sharing an APR pair with the input of a scrambler UT. And now we know that Bob should measure any output subsystem D in order to learn how to scramble this information. So without loss of generality, Bob can measure poly operators on D. Why? Because poly operators are a basis of any Hermitian operators in a subsystem D. So without loss of generality, let's talk about poly operators, PD. If we consider the adjoint action of the scrambler over these poly operators, we'll not get a polystring again, because this is a property of Clifford circuit, not Clifford circuit polluted with number T of T gates. However, what is surprising is that every doped Clifford circuit admit a subgroup GD of UT of the polygroup PD that includes all those poly operators which are sent by the adjoint action via UT in poly operators again. So let me make an example. Let's say that T equals 0. So this is our entire Clifford circuit. Then GD of U0 is exactly a polygroup on D. So we have a lower bound on the sides of this group. So the number of elements in this group, which is the same dimension of a polygroup on D, and every T gate thrown in a circuit at most half this dimension. So it's T squared divided by 2 to the T. Okay, so the idea of the algorithm is to use only operators in this GD of UT and mock the inverse evolution with a Clifford circuit. Being more precise, if you consider any poly operators in this group, since the adjoint action of UT on PD is a polystring, then the action can be replicated by a V prime, which is a Clifford operator. Thanks to the unitarity of both these unitary, there must exist a Clifford operator V prime that obeys this relation for any PD in GD. And now you know, by multiplying this and this on the left, you realize that V prime is exactly the inverse of UT restricted on this set, on this group here. So the idea is that Bob must in some way look only at the operators here and retrieve the information as well. Okay, so first Bob must learn GD of UT, and this will be the exponential part of the learning algorithm, and we'll see how to do it. No, we won't see how to do it. I will claim that it's exponential. If we want to see how to do it, I can show you. Anyway, let me make a simplifying assumption to claim why Bob can look only at GD and how to look only at GD and retrieve the information in a Cliffordized version. So let's make the hypothesis that there exists a Clifford operator that I call D, because this is called the diagonalizer operation, that maps the entire group GD into a subset, into a polygroup on a subset E, which is strictly less than D. So a subsystem of qubits C, which is within the qubits on D. And let's make the assumption that there exists a Clifford operator that maps this group here. Of course, in order to exist this Clifford operator, GD of UT must have some structure which depends on UT. And there exist unitaries that have this structure, so it's not a wrong assumption. Okay, now, of course, since we have this bound to the cardinality of the group, we also have this lower bounds to the size of E. Now, if Bob is able to measure only operators, whatever operator he is, because a polygroup on E are a basis on E, the scramble will be completely undistinguishable from a Clifford operator. Let me explain why here you see a red line, here blue, because E contains all those operators or expectation value, which if you measure, the scrambler is indistinguishable from being a Clifford operators, while F contains the non-stabilizer information of this scrambler here. So the fact that Bob can learn by looking at this subsystem can be true because of the decoupling theorem. Remember, Bob can learn everything about Alice by looking at any subsystem, provided the subsystem is slightly greater or bigger than A. But in order to do so, it needs to completely erase this non-stabilizer in this information in an efficient way. So it needs to forget about F in a unitary fashion. How to do so? Well, we're talking about scrambling all the time. Scrambling is exactly about forgetting and hiding information into a bigger subsystem. So what's the best way to forget or trace out non-stabilizer information? That applying some very bad scrambling unitary on F. Indeed, the whole protocol is this one, which is a bit ugly, I should admit. But let's follow the lines, and I guess we can go through this diagram. So there are three main objects in this algorithm. The first one is the diagonalizer that splits the space into preserved polyoperators and non-preserved polyoperators represented by F. The red line. Let's follow the red line, which is the information we want to hide, we want to erase in the learning process. Indeed, the red line goes through this second main object of the algorithm, which is the randomizer, which is just a random Clifford operator. We know that a random Clifford operator attains a very small value of the 4-point TOC, so it's very scrambling. And so the information in F will be spread throughout the system. Mind that the other input system of this R is C prime, which has the same dimension of C. So there is an interplay between the size of the dimension of T and the size of the dimension of C, because their sum must be N. And that's why the probability of decoding decreasing the more the T gates there are. But we will go through it again. Okay, so this randomizer has the task of hiding this stabilizer information here, and then the output here goes again into the dagger. Remember, the star is the dagger in these drawings of the diagonalizer. So E is completely untouched, and the diagonalizer dagger makes this information back together. Now I claim here, since F has been forgot, here there's only stabilizer information. Indeed, if now Bob employs a pseudo decoder, which has just the task of mocking the inverse of the scrambling UT on GD of UT, Bob retrieve all the information. And the final decoder, of course, is the composition of these three objects. So there is the randomizer twirled by this diagonalizer here that needs to split the space, forget one, and then put them together again. And then there is the pseudo decoder, which just mocks the inverse scrambling unitary. Okay, what is the cost of learning these three? These three objects can be learned by an algorithm that measures only D. Because as you can see, the only part that is using C is a random one. That it's just built at random. So as you can see, we only care about D, being the inverse on D and diagonalizer splitting D. Okay, so the costs are the following. So first of all, Bob must identify the preserved Pauli's GD, and this has the cost exponential in the number of T gates, but polynomial in the number of qubits. Then once Bob learned this diagonalizer, this GD, learning the diagonalizer is very efficient. Learning a pseudo-decoder is very efficient, and the fidelity of the pseudo-decoder is, this one is 1 minus an exponential in this 2D minus t, while the probability to forget via the randomizer is the opposite, is 2n minus 2D minus t. You can see if you plug in here t equals n, there's no value of d that makes these two quantity 1 at the same time. One of those should decay exponentially with d. And so that's why, this is exactly the reason why the algorithm breaks down after a number of T gates that cross the barrier of n T gates. So again, in the classical regime, the Clifford decoding is possible, it's polynomial in the number of qubits. In the quasi-chaotic regime, it is still possible because you can always find a value of D which is suitable to make these two numbers 1 at the same time, but it's exponential because you, at the end of the day, you need to learn this GD, which takes exponential time. And in the chaotic regime, there's nothing to do with this algorithm, of course. Okay. So again, what we use? We use that we are able to move non-Cliffordness with the Clifford operation. Why? Because non-Clifford is encoded with an entropy. I don't know if you heard about the stabilizer entropy, and the entropy can be moved around with Clifford operation. We preserve the amount of entropy. We are able to forget the non-Clifford part because Clifford group are very good scrambler, and scrambling is a tale about forgetting information by a unitary process which is hiding localized information into a bigger system. And then we exploited the power of the decoupling theorem, which says that we can measure, once you have a scrambling unitary, you can measure every subsystem and contains, together with the Bob's qubit, every information about Alice. And all these three ingredients serves that up to t equal n, the algorithm works. And the scrambler is Clifford reversible. So the only outlook I would like to give you now is the fact that moving the non-Cliffordness around, and it identifies a subgroup of the polygroup, local polygroup, which is clean by magic or no stabilizing resources, reminded me to the concept of the coherence-free subspaces. So the coherence-free subspaces, imagine you have a system in contact with the bath, you have an interaction Hamiltonian. Whenever in your system there is a subspace that commutes with the interaction Hamiltonian, this means that this subspace is not affected by noise and by decoherence made by the interaction Hamiltonian. Here is the same, kind of the same thing. We are identifying, we are treating magic resources, T gates, as noise during the learning and unscrambling process. And what we do, we identify a space, which is very costly to identify such space, but we identify the space magic-free, and then clean those subspace from magic resources and read the information in a clean and Clifford way. Okay, I think I finished. Thanks for your kind attention.
Yeah, Lorenzo, thanks for your very interesting talks, and yeah, everything that you did is kind of like intuitive. And so far we didn't have a question from the audience. Maybe for the audience, if you have a question, then you can type it in the chat, or you can like raise your hand and unmute yourself and ask the questions. In the meantime, actually, I have questions for you. Basically for clarification for this one. Like for the decoders and the randomizers, like what gates do you use to put it? Is it still like Clifford circuit? Clifford gates for the decoders?
The question is, are these guys Cliffords?
Yeah. As in, maybe I missed that. Yeah. So V is definitely Clifford, right? But then it's like for D and R, is that still Clifford?
Okay, yeah. D is Clifford. Why? Or at least can be Clifford. It's not So there exists other unitaries that are not Clifford with this property, but can be Clifford because this constraint is just on poly operators. Because this is a subset of poly operators, and this is another subset of poly operators. We have this condition, and so can be Clifford operators. And the randomizer can be Clifford operator because the only request that we are doing is that it's very scrambling. But Clifford operators are very scrambling. So all of these blue boxes represent Clifford operators.
Right. Okay. I see. Okay. So I have the other questions is now because you kind of like add more so your like the parameters in your formalism is basically t, right? The number of like t gates that you add into the circuits, the t dot circuit, right? Then the larger the t, then the more scramble your like system will be, right? And then I remember like recently people have studied a so-called measurement-based induced measurement-induced like phase transitions where that will make kind of like measures like do projective measurement randomly like with probability of p, and then basically the projective measurements will kind of like disentangling the system, right? I'm wondering like what happened if you add in this factor in, and how would it affect your protocol, as in like because over here if for your p if it is large, that means like it will kind of disentangle your qubits, and if it's small then you just kind of like have like kind of high degree of scrambling. And like I'm just wondering like how is this measurement probability competing with the parameter t that you consider over here. I hope that I kind of like
That's a great
explain the
question.
correct.
I have no
Yeah.
idea. I have
Yeah.
no idea. That can be a thing or maybe not. I have no idea actually.
Yeah, because I know it's like they basically like they started off with just like, okay, I have a quantum circuit and then I could apply random like unitaries on these qubits, and then it's like the more unitary that I kind of like apply on the circuit, then the more scramble that the information would be at the end of the protocol, right? And then it's like they're just not like, okay, like what if we add in more measurement, like just do a randomized measurement, and there will be a critical like probability of measurements that you do that will kind of like make the phase transition happens. If the probability greater than this critical value, basically like the output state will be disentangled, kind of like like the entropy will be low, for example, or maybe the entanglement will like obey the area rule of entanglement, and if like the probability is less than this critical value, then it will observe the volume law of entanglement. Yeah, I'm just curious on like how
No. It's a very interesting topic, and it also has a tight relationship with another phase transition in stabilizer entropy. So this undergoes a kind of a phase transition in some way because you are.
Sorry, can you explain a bit about the stabilizer entropy? What is it about?
Oh, okay. Yeah, sorry. So the stabilizer entropy is a property possessed by quantum states.
Mm-hmm.
Okay, if you measure the expectation value of every poly operators,
Right.
you get a tomographic description of the state, right?
Mm-hmm. Yep.
Okay. And if you sum this expectation value square and divide it by d,
Mm-hmm.
you get 1. So you get a probability distribution because these numbers are positive, real, positive, and sum up to 1. The entropy of this distribution is the stabilizer entropy, and is an efficient measure of magic from the resource theory point of view. Okay. Then is tightly related to this protocol, because indeed you can show that there is a phase transition in stabilizer entropy when you move your T gates away from the system D. And so your question is very interesting because there is a phase transition here that we showed in a subsequent paper of this, and a phase transition showed by the Maryland group. You're referring to the paper in the Maryland group.
I think so. Yeah. Mm-hmm.
And I think it's very interesting. The question is there a relationship between those two phase transitions? Yeah, maybe. Yeah,
I
I
don't know, as
agree.
in I'm not expert, as in I just like came across these papers and think that this might be relevant. Yeah, so that's why
Well,
I
maybe
asked.
for sure you can find a relationship. What then we need to see whether it is interesting or not, this
Yeah,
relationship.
yeah, of course, yeah, definitely. Just like just some random question from my
Yeah.
I remember like at the end you kind of mentioned about some noise or whatever, as in like I couldn't catch it. Like, okay, so if you have some decoherent noise, how would it play out in this like protocol? Because like over here you assume everything is kind of like perfect, and yeah, how if like you have some decoherent kick in at some point in your like protocol, like how would it affect the
How robust
successfully?
okay.
Yeah,
So
how
is the
robust? Yeah, yeah.
okay. Is the question what's the analogy with the coherence-free subspace? No, it's not a question. The question is how robust is this protocol against noise?
Yeah, 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 that's right.
It's very fragile
Okay.
because bell measurements are very fragile.
Uh-huh.
Bell sampling is very fragile with noise.
Mm-hmm.
Indeed, quantum teleportation is not very robust with noise and all this.
Okay. Mm-hmm. Oh, I
Fragile.
see, I see.
We
Okay.
live in a quantum mechanical and unitary world here. I'm not
Yeah,
caring
yeah,
about
I see. Okay, yeah, as
biases.
in like no, as in like that's fine, right? As in like we were starting off with a spherical count and then we just like adding more details and trying to see like how these protocols will works in a realistic way. But still like this result is very interesting because I never like thought of like using uh just like learning the kind of Pauli mappings of the unitary, then you'll be able to control the Clifford circuit to basically uh kind of like construct a like decoder to like decode the information out from the system. Yeah, it's very
There is
interesting.
a work about disentangling scrambling by the coherence because they are kind of distinguishable.
Okay.
Because scrambling is erasing information in a unitary way. The coherence is erasing information in a non-unitary way. So they're kind of distinguishable. This work is from Yoshida. Is a PRX quantum, I guess. Or PRX.
Mm-hmm.
And they also have an experiment, but it's not this teleportation protocol. Just, you measure the mutual information. They found a turnaround about this indistinguishability, but it's not very robust as well. I need to say. So
I
yeah.
see. Okay, great. Yeah, I think that would be
Yeah,
all
thanks
question
for the
from me.
questions.
And we didn't have a question from the audience. Maybe they just need some time to think about the question. They might email you if they have more questions.
Yeah,
But
no worries.
still, thanks again, Lorenzo, for the very interesting talks and like address all of my questions.
Yeah.
And looking forward to have you again in the future. Yeah. Yeah.
Thanks very much.
Yeah. Then
Yeah.
we will end our seminars like now. And thanks for your time. Like, see you guys. Bye.
Bye.